2 minutes. All right, it's 11 a.m. Let's get rolling. Maybe. There we go. Okay. Before we start with prayer, I wanted to let you guys know. So I think a majority of you probably know Professor Collins. Yes? Yeah. He was on vacation with his family in Hawaii, and he had an injury where he injured his neck doing boogie boarding last week. And so he is laid up in Hawaii right now, injured. He's not any worse for wear. Every doctor says he's doing well, but I wanted to let you guys know so you could pray for him and his speedy recovery. Okay. And so just so you guys are aware. All right. All right, so let's get into it. Lord, thank you so much for everything that you do for us. Thank you for allowing us to come together today. We pray that you would help us all to put aside the things that we know aren't that important and have us come together to pray for Professor Collins' healing. Help him to stay strong, get better, and to make it back to the mainland as quickly as possible. In your name we pray. Amen. All right, so I did text with him. He's doing okay. They're just at this point stuck until the doctors clear him to come back. So, all right. Another announcement before we jump into stuff. I will not be here on Thursday this week, but I have secured a rather talented replacement in my absence, and Professor Tomford is looking forward to spending 2.5 hours with you guys on Thursday. So fear not, fear not. Okay, so we're going to recap. We're going to go over the quiz. I have not finished grading the quiz. We'll talk about it in a second. And then we're going to keep going through method of joints today and probably introduce method of sections. That's the thing. So from the last time, not the quiz, right, but the class before the quiz when we started talking about method of joints, right, which is I mean, I'm basically asking you guys to remember stuff from exactly 1 week ago. It's rude and it's evil, right? And how can I possibly request that? There was a whole Memorial Day weekend in between that. Um, Seems like everybody was doing pretty okay from method of joints. So the thing, we'll go over it again in a little bit, right? Method of joints really does break down to a bunch of 2D problems that rely on you solving them in order, right? So if you feel comfortable with a 2D problem, right, which most of you do based on things that I've seen, you should be pretty comfortable with method of joints. Okay. But we'll keep going through it later. Is there anything that anybody has a specific question on right now before we jump into some of the other things that we're going to do? Yeah, Jace, what's up? I will hopefully have them done by Thursday. That's my plan. I'm about halfway through them right now. Any other questions? Yeah, Caleb. I don't know. That would require me to do that midway through. With all the zeros, since I haven't graded half of them, it's at least 50%. If, and I normally I'll wait, I'll make this announcement now. If you can't possibly wait to get your quiz grade, you are more than welcome to come to my office to see your quiz, but you have to take whatever grade is currently on it. That stops my grading. So if none of it is graded, you get a 0. Or you guys could just leave me alone to grade the quizzes. One or the other. Okay. Um, this is recap from last time, right? So just as a reminder, right, we were talking about analysis and design assumptions for method of joints specifically, right? And the two assumptions that we are going to most commonly make, which is really three because that's how sentences work, right? Are that all of our loads are applied at the joints. We neglect the weight of the member of the truss, and all the members are joined together by smooth pins, right? So we have pin connections joining everything together. All of the loads are going to be applied directly at the joints, and we're not worrying about the weight of the member, right? That's not something we care about. And the final assumption that's not really on there, right, is that we're going to assume that if we don't know, we're going to draw everything in tension to start with. And then we will change it as we go. All right, here's the things that are due up until quiz 2. I will update this next week to reflect the rest of the things that are due. Guys, we are in week 4 of a 7-week class. So we are over the halfway point. Jaden, what's up? Okay. Well, then I guess it's what's the 5th is our quiz, right? We'll split the difference. I'll give you to the 4th. Fine. I really, since this is homework that is on the next quiz, I don't want you guys to have not tried it until after you've taken the quiz. And so I would very much prefer that you have done it before you go into the quiz to help you be prepared for the quiz. I will tell you right now, if you don't do homework 4 before the next quiz, or at least look at it before the next quiz, you're probably not going to feel like you've had enough practice with problems that look like stuff from homework 4, which will be on quiz 2. Because quiz 2 covers homeworks 3 and 4. Okay. I'll update it in Halo then, and I'll put it on the 4th. If you don't see that change, send me a message, because there's a chance I might forget. All right, cool. That's things to do. Do the things that are due. Please start your CLC presentation sooner rather than later. I would like you guys to know that June 1st is this Sunday, which means that you have roughly 3 weeks left for this project, right? Next week, we will talk a little bit about SolidWorks and how to find it, and how to do trusses in there, right? We'll talk a little bit about it, and I will send you guys some good external videos that really you can take some time to kind of dig into as well. Some resources, if you will. But we'll talk about that next week. Here it is this week. Never give up. Don't. You don't ever give up. All right, there you go. It's pretty self-explanatory. All right, let's talk about the quiz. I'm going to say the thing that all the professors say is that I really thought that this was a fair and balanced quiz. Um, I didn't think like I hit you with anything crazy. There was no like curveballs and stuff. We'll talk through it in a sec, right? Um, I thought, if I'm not going to put the whole story for each problem on here. That's so just the relevant parts, right? But I felt like I really captured the Despicable Me vibe for this one, personally. So there we go. All right, so here it is. The first question, right? Here's figure one. The hook has two ropes connected to it, one with a force of 100 newtons at 15 degrees to the horizontal, the other with a force of 150 newtons at an angle of 10 degrees to the vertical. So tricky. Angles that are given off of different axes. How dare I apologize. Use whatever method you see fit to determine the resultant force. So you use whatever method. What is that? You use trig, you use parallelogram, you can use triangle, right? Do whatever you want to do it. It's fine. You get a bonus 5 points if you use one of the other methods to check your work, right? And we'll get into that in a second. So this one, for these quizzes, right? There was also one thing I probably should have put up there, right? So the first question was fill in the blanks in the problem statement, right, where Vector introduces himself. I commit crimes with both blank and blank. It's magnitude and direction, or direction and magnitude, whichever order you wanted to write them in. It's a very nerdy joke that the writers of Despicable Me made, right? Because why? Because vectors have magnitude and direction. So he commits crimes with both magnitude and direction, with purpose and anyway. Write down your knowns. All right, so let's get a pen out here now. Go. Maybe? Is my pen still here? It's over here now. Wow. All right, so what do we know? First thing that we were asked for outside of that are knowns. Well, we know that F1 is 100 Newton, F2 is 150 Newton. And we know the angles, right? I just wrote the angles like that. We were 10 and 15. What were we looking for? Our unknowns, or what we were looking to find is the resultant vector, right? It said the resultant vector. There's two parts to a resultant vector. We need to have its magnitude and its direction. You can write it. I told you guys in class you can write it either in the Cartesian or the rectangular form where you have the ij components listed out, or you can go a step further and actually find the magnitude and the angle from one of the axes. Either way is fine. Free body diagram. Well, let me do it this way. Here's my point. That one was F1. Here's F2. We know that that is 15 degrees, and this is 10 degrees. I think that pretty much does it. Just for completeness, rotations aren't going to matter here, but there we go. Right. So if you had this or some version of this drawn on your paper, good job. You did it. You got 10 points. Okay, so then the analysis part. So what do we do if we want to get the result? There's a couple ways you can attack this, right? You can write out what the force vectors are in their x and y components, right? And then you can sum the force components in the x direction and sum them in the y direction and then put them all together. You can list what the vectors are individually, right? You can solve f1x. The way that I did it was I started by summing the forces in the x direction. And I said that if I sum the forces in the x direction, I get a, well, that's, I didn't want to say equal to. I'm going to start by summing the forces in the x direction, right? Start with my x direction. So I've got F2 times the sine of 10 degrees. I guess F2, I have F1 and F2 confused here. Let me just double check. Yeah, I wrote them backwards in my drawing. Oh, minus a point for Dr. D. One, there. There we go. Right. Some of you went the extra step and just made that 80 degrees from the horizontal because you didn't want to deal with having different sine and cosine, right? Because your OCD is showing. That's fine. Um, right. So, and then if we look at the y components together, right, we get, okay. Right. So now we have everything else. Now we just plug in the forces and solve, right? So if I look in the x direction, if I plug in, I have 150 sine 10 degrees plus 100 cosine 15 degrees. You put those in your calculator, hopefully it was in degrees, and you get 122.64 Newton. Do the same thing in the y direction. And you will get 173.6. I am carrying to 2 decimal places for now, and that's fine. I did not specify how many decimals. If you rounded up to have just whole numbers with no decimal, that was fine, right? Again, I am less concerned. I said this the day before the quiz, right? My concern is less about what you getting the correct answer and more about me understanding your thought process, right? So small mistakes, say kept it as F1 and F2 flipped. I would have gotten hit up in this. I would have gotten like a few points off, but the rest of my solution is correct based off of that change, right? Right? All right. So now last step, we got to put it together if I want the resultant, and I do because that's what I was asked for. And I'm going to take the easy way here and call it a day. Some of you decided that instead of doing that, you were going to write the angle and the magnitude. The magnitude, something like 213 newtons at 54 degrees, something around there. So, and that's great. Okay. So that's how I did it the first way, because I certainly wasn't going to just go right after it with triangle or parallelogram. But if I wanted those sweet, sweet bonus points, I needed to do it the geometric way. Now, some people I saw tried to do it did it with basically did it in reverse and started with the result and then decomposed it into F1 and F2. But that doesn't really prove that what you did was correct. It just proves that you do the same steps in reverse that you started with, right? It's not an independent method for doing it. So if we wanted to do it, right, with our triangle method, which I'm going to, here's my point. I'm going to draw my axes here. And I'll start by drawing F1. And F1 is going to be roughly 15 degrees, right? Or it is 15 degrees. I will draw it at roughly 15 degrees. There we go. That's that. Then we take our second vector, F2, and we are going to draw that from the end of our first vector. So we draw it at 10 degrees off of the vertical here. So it's going to be basically straight up, like right there. That's F2. And this angle here is our 10 degrees. And then our resultant connects the two from here to here. And I'll call that FR. Okay, so we have to do a little bit of geometry here, right? So what do we actually know? Well, let's break this down a little. If I extend this along the line of action of that force, right? I know that this has to be 90, well, not 90, sorry. I know that if I keep this flat, this is 15 degrees, right? If I want to go all the way around to here, that's 180, right? From there to there, yeah. I also know that from here to here is 80 degrees because if I was to go all the way to the vertical, it would be 90. So if I back it off 10, it's at 80. Okay. Why is that important? Because it lets me get this angle in here, which is 65 degrees, because it's 80 minus the 15. Then 180 minus the 65 gets me the angle in between the green and the blue, right? So from here to here, that should be 180 minus 65, which is 115 degrees. All right. So you have to kind of piece together what the angles should be. Everybody tracking, making sense? Makes sense to everybody? We good? I'm going to label this one alpha and this angle up here beta for reasons. Then we got to do, well, if we want the magnitude, right? We just want the magnitude, FR. We can find it directly using law of cosines. I'll call that gamma. Okay. So what are A and B? A is our is F1 and B is F2. Notice what happens when cosine is 90 degrees. You get Pythagorean theorem. That's law of cosines. All right, and if you plug all that in, you get 212.55 Newton, which, like I said before, if you were to go back and take our original vector, 123 plus 174 square root of the sum of the squares, you get 213. So right there. Then we need the angle. So what do we need? We need the angle off of, we need alpha plus the 15 degrees, right? So how do we find alpha? Well, the sine of alpha divided by F2 is equal to the sine of 115 degrees divided by FR. Law of sines. We can solve this for sine alpha is F2 sine of 115 divided by FR, or that alpha is the sine inverse or arc sine of, what's that, F2 is 150, sine of 115 degrees divided by 213, and that should give you 54-ish degrees. 54 and change, but it doesn't round up. We'll leave it at 54. No, sorry, that will give you 69 degrees. No, sorry, wait for it. Let's just do it. Okay, there. So that will give you 40 degrees. And then you add the 15 to it to get the full angle, right? Because what is this angle? This is alpha, which is the angle between the F1 vector and the resultant. But if we want the from the x-axis, we need to add 15, which gives us 55. There we go. Great success. We did it. Any questions on this one right now? No, we good? We good? I mean, that was worth 30 points, that whole problem. And you guys had the breakdown, so you know what each section was worth. All right. Okay. Well, here's the second question then. Surprise, surprise, there is a 3D equilibrium problem on here. Not really a surprise. You guys should have expected this. And to boot, it's one of the ones that's going to need us to use unit vectors, maybe. There's a second way you can do this too. And that's fine. All right, so figure 2 shows you a package that weighs 500 pounds. The issue is that none of our engineers can determine the force in the cables that will allow for static equilibrium. Your mission is to determine these forces. So you need to figure out the force in the cables. Okay. This one was worth 65 points. Lots of points on the line for this problem. Bless you. So where do we start, right? Well, first thing I asked you for was the knowns. Like we start every problem. We know that the weight is minus 500 k-pounds. And we know distances, not angles, just distances. Things that are unknown or that we're being asked to find are the forces in CA, the force in CB, and the force in CD. Okay. Next, we were asked to draw a free body diagram. Here's point C. We have our weight. That's going to be pointing straight down. I've got some force F, C, D. I'll say, hey, point D is going to be over here somewhere. All right, then I've got some force FCA. I'll draw over here, FCA. And point A is somewhere over here. And then the last one is FCB with point B being somewhere over here. All right, and so the way that this was drawn had our y-axis this way, our z-axis upward, right? And our x-axis coming this way. Right? And it's obviously not drawn to scale, but here we are. Just so that we understand everything a little bit more clearly, I will have an extended, well, I'll draw it the actual correct way, not that way. So we have that, right? No rotations that we need to worry about. We do have to put our distances here. The distances are to the points, not to the end of the forces, although they could be to the end of the forces because you can draw the force vector to be as long as you want. It's an abstract idea. The important thing is that it's drawn in the correct direction. So in this case, in the y direction to point D, this is 6 feet. And in the z direction, that's 8 feet. This is 2 feet, and this is also 2 feet. And in the y direction, we know that this distance is 6 feet. And that's our free body diagram. Nailed it. 25 points for that. 25 points to draw that free body diagram. Some would say generous. Okay, that's great. Now what? Well, you can do this a couple of different ways. I opted to do it with unit vectors, which is how I'm going to show you how to solve it right now, okay? Which is also the way that we would have done it in class. However, some of you did notice that, from what I've seen so far, if I go back, some of you noticed that all of these are in a single plane. They're not, right? This is just in the YZ plane. This is just in the XY plane. And so some of you did it the trig way because you can, because you have the way to identify all of those. And so you just did that, okay? Because there's a 0 component for each of the forces in those directions. But I'm going to do it with, turns out, I will tell you that it takes about the same amount of work to do it either way, right? Because if you're going to do it correctly with 2D, a bunch of 2D drawings, you really want those FBDs in 2D of them. Otherwise, you're not going to stack your vectors correctly. Okay, so I started by developing the unit vector for CD, which is the distance from C to D divided by the magnitude of that distance from C to D. All right, if I'm going from C to D, well, there's no travel in the X direction. I have to go positive 6 in the J and positive 8 in the K, divided by the magnitude of that. And the square root of 6 squared plus 8 squared is 10. Right? Divide by 10. And so our unit vector, I'll write it up here just so we can have it for tracking. 0I plus 0.6 J plus 0.8 K. Right? Now we're going to do the same thing from C to B. Remember, the directionality matters, right? Because we are pointing these vectors from C. Why? Because they are cables and they have to be in tension. They cannot be in compression, otherwise your system is not working, right? So how do I get from C to B? How do I get from C to B? Well, it's going to require some movement in the X direction. It's going to require me to go -2 in the X or in the I. And it's going to require me to go -6 in the J, but 0 in the K. And if I take the magnitude of that, some of you wrote it as root 40 and left it as such, which is fine. I prefer to have it as 2 root 10. It's the same thing. And if I square it, it's 4, and then I can put it under the root 40. Okay. If you wanted to, you could clean it up, right? And you could make it negative I minus 3j over root 10, right? That's the same thing too. There's many different variations of how you could have written this, and that's fine. Including this, which is going to look gross, and oh, never mind. We're done. Including this one. Oh, no, we're not going to. Technical difficulties are starting to tick me off just a little bit. Just a little bit. Okay. And then guess what? We'll do A now. The fun thing about A is that that vector looks pretty much identical to the CB one, with the only difference being that it's positive in the x direction instead of negative, because they're in a line together, right? That's it. And so really we can just take this guy. No, you're not gonna let me do it. Come on. Come on. That would have been so good. Apparently copy and paste is off the table in Zoom. I'll write them a message about that. And the last, yep, and that's it. Those are our unit vectors, right? Cool. Everybody cool with unit vectors for that so far? Again, if you didn't do it with unit vectors, it doesn't mean that you didn't do it correctly. There are other ways to solve this. If you really wanted to do it with trig, you could have. But I would argue that it's roughly the same amount of work either way. Okay. Nothing? No questions so far. We good? Okay. So what we do now? Now we develop our forces. One of the things that I've noticed so far while grading is that sometimes people use F for their unit vectors. Please don't. It's not a force, it's a unit vector. Um, it doesn't really matter what variable you use. You can use F if you want, but then when you go down to solve your forces, if you use F there too, it becomes very confusing. So use different variables for different quantities, okay? That is more so for you to not get confused when you are looking at your stuff later, and you don't have to be like, can somebody else explain to me the work that I have done? And the answer to that is no, nobody else can, because you're the one that did it, and you need to be able to understand it. Anyway, how do we get the forces? Well, force is just the magnitude of the force times the unit vector. So if I want to write down my force vectors, if FCD should just be, let's see, 0 in the I plus 0.6 FCDJ plus 0.8 FCDK. And we'll do the same thing for FCB, which would be negative FCB root 10 over 10 in the I minus 3 FCB root 10 over 10 in the J was 0. Okay. Hey, Matt, a little loud. All right. Thanks. Okay, same deal, going the other way. This one should look real similar to the one we just wrote down. The only difference is that the x component is positive. And the final vector that we need is our weight vector. Not negative 1500, but negative 500. Well, let's write it out just like the other ones for fun. 0i, 0j, minus 500, k. Right, and these are all in pounds. Now we're ready to go, right? We've got everything set up the way we want it. Some of the forces in the x direction, some of the forces in the y direction, some of the forces in the z direction. I'm gonna erase my FBD for now, so I have a little room to write the rest of this stuff, and we can still see the vectors. So if I sum my forces in the x direction, I get negative FCB root 10 over 10 plus FCA root 10 over 10. The root 10 over 10 goes away, right? And so I just get FCA is equal to FCB, right? Keep that one as equation 1, moving along F in the y direction. Looking down, this one's going to be a little bit more convoluted, right? But it's okay. Yep. 0.6, yep, yep. Nothing in the J there. We're going to leave that for now because there's really nothing I can do with it. But the next one, FZ, will be really nice because I only have two things in the K direction. I've got 0.8 FCD and the weight, minus 500. So we can solve that right away. FCD is 500 divided by 0.8, which is 625 pounds. That'll be pointing up to point D, from C to D. Okay, we go back, right? And we're gonna have to do a two-part substitution into equation 2 over here, right? So pick whichever one you want to sub in for. You want to sub in for A or for B, it doesn't really matter because they're equal. So I subbed in for FCB with FCA, right? And so if you do that and you rearrange some things, you get 0.6 times 625 is equal, right? So and then I move the other two over to the right-hand side because they're both negative. So if I make them positive and they're both FCA, I end up with 2 times FCA times 3 root 10 over 10. And you can say, well, why didn't you just make it 6 root 10 over 10? Could have done that too, right? It turns out that if you solve this for FCA, right, you end up with 197.64 pounds. Notice it came out positive, so we assumed tension correctly. FCA should be going towards point A, and then FCB is just equal to the same thing as FCA. 64 pounds. This one headed in that direction. And there you have it. Right. Pretty straightforward, right? Again, if you wanted to do it with trig, you could totally do it with trig and it works out It's fine. Questions on that one? Mhm, mhm, mhm. Nope. 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 Okay. Well, all right. Next, next one, I guess. Okay, this one, 30 points for a bunch of unit conversions. All right. Biggest mistake that I have seen so far is just flipping the conversions, not using multiplying when you're supposed to divide or dividing when you're supposed to multiply. All right. Um, that's the biggest thing that I've seen so far, right? All right. So let's start here. Water has a density of 1.94 slug per cubic foot. Also, I will show this off right here. Pound per square foot is not the same as PSI. So if you solve this in PSF or PSI, I gave you points for it. I did not because I messed up. So that is an error in your favor. So you could have had, there's two possible answers for this particular conversion based off of the fact that I messed it up. And that extends um, that does not extend down to the part B for this one because there is a direct conversion in that chart that you guys had that will take you from um, PSI directly to Pascal. Okay. Anywho, let's walk through it. So we have 194, or not 190, 1.94 slug per cubic foot. All right, and we need to convert this into density in SI units. Great. What are the SI units for density? In general, what's a density? If I asked you to write the equation for density, what would it be? Yeah, mass divided by volume, for sure. Right? And so what's the SI unit for mass? Bless you. Kilogram. And what's going to be our SI unit for volume? So, I mean, get technically liter, I suppose. But if we were looking at like the volumetric capacity of a cube, you could do centimeters cubed, you could do meters cubed, right? That's looking for density per length cubed here, right? Given what we have here. Okay, so first thing I want to do is I got to get rid of the slugs. So there are 32.174 pounds mass per slug. That one came directly from the chart. All right. Then we want to get from pounds mass to kilogram. There's 1 kilogram for every 2.205 pound mass, again, directly from the chart. And then we have 1 foot cubed, which is 1 cubed, 3 feet cubed, right? Bless you, divided by 0.3048 cubed meters cubed. Right? And that gets rid of our pounds mass. This gets rid of our feet cubed. And so what we're left with are kilogram per cubic meter. And when we multiply all of this together, we get that the density of water is equal to roughly 1,000 kilogram per cubic meter, but I wrote it as 999.66 kilogram. per meter cubed. Right? If you did it in centimeters, that was fine. I'll allow it. It's a valid measurement for that. This checks out with hopefully what you guys recall as the density of water from chem, right? Or thermo, if you've taken thermo, right? Or really any science class that requires you to use the density of water for any reason. It doesn't change depending, but changes depending on temperature and pressure, but you know, anyway. Anyway, okay. That was the first one. The next one, the Pascal is actually a very small unit of pressure. To show this, convert 1 Pascal, which is 1 Newton per square meter, to PSI, which I then labeled incorrectly. My bad. Get myself some room here. All right, so if I have 1 Pascal, which is 1 Newton per square meter, and I want to take that to PSI, well, I'm going to need that to be in pound per square inch or pound per square foot, depending on whether I use PSF or PSI because Dr. D messed up. Great. So how do we start? Well, first, we're going to convert our newtons to pounds, right? And so there are 0.225 pounds per newton, or 4.448 newton per pound. Those are the same, right? It's the same. If I go 1 over 4.448, it should get me the 0.225. Newtons go away. I'm left with pounds. Okay. Now I need to get down to square inches or square feet. If I'm going to square feet, it's 0.3048 squared meters squared per square foot. Right? And if you were to cut it there, you get 0.0209 PSF, or pounds per square foot, which nobody reports pressure in pounds per square foot, but that's one of the possible answers for this question. If we wanted to take that to PSI, we know that that's pounds per square foot. That means that I've got 1 square foot for 12 square inches squared, right? 12 squared inches squared. Gets rid of that. And this is going to give me 1.45 times 10 to the minus 4 PSI. So it's a really small amount of pressure. Right. Great. The next one, you could either do this in reverse or just use the 6,895 number from the table, right, to go back the other way. I'm going to do it the long way because reasons. Because I did it the long way. Because unit problems are fun. 14.7 in PSI. And I need to bring this to pascals. First thing I'm going to do is convert Newton using the same conversion factor that I used above, just flipping it to get rid of the pounds instead of using the newtons. Then we need to convert this from inches to feet. I mean, you could go directly from inches to meters if you wanted, but I just used the same things that we did in reverse, right? Okay. left with Newton per square meter. This is going to be a really big number, right? I know that because I'm dividing by something that's a decimal being squared. So it's going to be much larger than 14.7. And in fact, comes out to 101.2, no, not point, 101,270 Pascal, or 101.3 kPa if you're using kilopascal, right? Depending on where you used your truncation and things like that, which hopefully also resonates because if the atmospheric pressure at sea level is 14.7, hopefully you remember that 101.3 is our standard pressure in kPa, right? For air. All right. Questions on these at all so far? We good? All right. These are the more interesting ones now, right? A man weighs 155 pounds on Earth. That's pounds force, right? Because it was not specified as pounds mass. But also, if it were pounds mass, think about how much that person would actually have to weigh in pounds force. It's a ridiculous amount. And I would argue that no human has ever weighed 155 times 32.2 pounds. That's that's pretty excessive. So context clues. I mean, I guess it's possible in, somewhere in the MCU that we could have that. All right, so we're going to start with 155 pounds, and we're asked to find the guy's mass in slugs, right? Because reasons. All right, well, guess what? There's one slug for every 32.174 pounds force on Earth. On Earth. That's the important part. On Earth, that's true. It's going to come into play in a minute, right? This gives us 4.82 slug. Okay, and that's also a nice number for us to just keep around. Okay, because we'll talk about that in a second. The next thing we want is what is the mass in kilograms, right? So we start with our 155 pound. Now I'm pretty sure that the table had a conversion from slug to something that was helpful, but you could also use the pounds to Newton conversion, which is what I did, right? So if I have pounds and then 4.448 Newton per pound gives me 70.28 kilograms. I'm going to hang on to that one for later. And part C for this is I've got my 155 pounds and I want it in Newton. Well, hold on. I did this is my Newtons up here. I was looking at the wrong spot. Like I said, that's Newtons, obviously. If I want to go to kilograms, right, the easiest way to do that is to take my Newtons and multiply by 1 over gravity. So if I have 70.28 Newton and I want to go to kilograms, well, Newton is also what? It's a kilogram meter per second squared. So if I divide by gravity, which is 1.9, sorry, not 9.81 meters per second squared, those go away, and I'm left with kilograms, and I get, sorry, I have to multiply. What am I doing? Dr. D, come on. Better than this. Or maybe I'm not. I don't know. There we go. Those cancel, those cancel. And we get 689.4 Newton. I don't know why I converted. Okay. I did this all backwards. That's why. Okay. Reset. 689.4 Newton. Take my newtons. 689.4 Newton. I want this. You know that this cancels with our meters per second squared, leaving us with kilograms, 70.28 kilograms. There we go. Got it. Nailed it. First try. There's no internet record to tell you otherwise. Okay, last part. On the moon, how much does this person weigh in pounds? Okay, there's a couple of things that need to happen here. Because now that you have moved to the moon, okay, and gravity has changed, you can either start with the 155 pounds, but then you have to remove the 32.2 and multiply by 5.3 to get everything together. Or you could say, I understand that mass does not change no matter where I am, right? And so the mass that we found up here in slugs is 4.82 slugs. And if I want to convert this to a weight on the moon, I multiply by my 5.3 feet per second squared, because a slug breaks down into pound second per foot, because it's gross. Okay? Oh, sorry, pounds squared. Pound second squared per foot, which is beautiful, right? Everybody loves that, which turns this into roughly 25.55 pounds, right? So remember, weight is just mass times gravity. If you know the mass and you know the gravity, just multiply them together, you're good to go. Second part we already did. What's the mass in kilograms? Well, the mass in kilograms is the mass everywhere. It's 70.28. We don't need to read. All right. That's what it is. Okay. Questions about unit conversions? Yeah, Colin. I will see what I can do about that. I will definitely look into that. I'll try to, things that you need, I will try to make it higher def for sure. I don't think you need everything that I gave you. So I will try to condense it where possible. Okay. And here's the last one. It's a fun fact about this particular problem. If you took ESG-162 with me, the only time that I ever taught it, this was actually a problem on one of your quizzes. Pretty much the same. I just flipped what we were looking for. That was it. And because the reason I did that is because I told you during that time that this was a statics problem, and it is. It's 100% a statics problem. So I'm just proving it. Anyway, in those problems, you're given the weight and you want to find the tension, but this time a little bit better. We understand that our tension is a certain number, and we want to figure out what weight do we need to put in there to create that tension, right? That's okay. And we're given these two angles, theta 1 and theta 2. Those are off of the horizontal, right? And you can tell that because they're put in this corner, which means they're indicating to you that those are the angles. And we went over that in class, right? A couple days before. All right. So first things first, right? We know the angles, theta 1 and theta 2. One's in radians, one's in degrees. The intent here was not to just have you flip the mode of your calculator, right? But to actually convert either into radians or degrees for one or the other, right? Yeah. So how much weight do we need to place in the hammock, right? So really we were just asked for W. This one was a little bit different. It didn't ask you for knowns, unknowns in an FBD. It just had you write, it wants you to write all the force vectors in a Cartesian form. So this was the setup part, right? We were supposed to acknowledge that we have some weight in this direction, right? We have some tension T1 that is going to be composed of X and Y components. And some tension T2. Right? And they should all be in pounds. Great. If I want to convert that angle into 1.2217 radians in 2 degrees, multiply by 180, divide by pi, gives me about 70 degrees. 70 and change, but close enough. We know theta 2 and we know T1. So let's start with T1. We'll write an actual vector for it. T1 is negative 500 times the sine of 70 degrees plus 500 times the cosine of 70 degrees. J and the I. Right. So you plug these in and solve for these numbers. You'll get this. Okay. And that's in pounds. So we have our X and our Y. So now we can do our I direction analysis, right? If I sum the forces in the X direction, set that equal to 0, I get what? Well, X components of things, I get negative 469.85 in the I, right? Plus T2 sine of 85 degrees. Can solve this for T2, right? Which was not specifically asked for, right? But you need it for the next equation to find our forces in the Y direction. So we end up getting 471.64 pounds-ish, right? Or sine of 469.85 divided by the sine of 85 degrees. And then in the J direction, if I sum the forces in the Y, set it equal to 0, I get 171.01 plus 471.64 times the cosine of 85 degrees minus W. So W, when we solve this out, is 212.12 pounds. That's the whole thing. That's the quiz. Great success. When I took the quiz, it took me, I had originally an extra, problem on there that I removed. The whole thing with the extra problem took a little over 30 minutes, but here we are. Yeah, right. That's what they say. Um, okay, cool. Any questions? Again, I'm planning to get them graded by Thursday. That is my plan. Everything updated. Just as a matter of course, I do not hand back exams. So if you want to come see it, you can come to my office anytime you want to come take a look at it. It has full feedback on it. I don't like exams getting out into the ether. That's just, I don't like it. Quizzes too. right? So, um, there you go. Even though all the solutions are here, that's fine. But, but yeah, you can come take a look at it anytime you want. Right? So, cool. Nothing else? Everything good? All right. All right. Well, in that case, let's revisit method of joints because it's been a week. And I'm sure you were all very concerned about method of joints over the weekend. But all right, so we have trusses, right? And we talked about this. We assume that all of the members have no, well, we assume that they're massless, and we assume that they're frictionless pins, and we assume that all of the forces are applied at those joints, which are pins, right? And so if we have a truss that looks like this, and somebody asks us to find the forces in each of the members and tell us whether or not they are in tension or compression, we do that, right, by drawing a free body diagram at each of the pins and solving some of the forces in the x direction and some of the forces in the y direction. As we treat the pin like a particle, and because we're allowed to rotate around the pin, we don't really worry about the moment. Right? We don't use the moment equation. Also, right, and so that's neat. Um, yeah. If we're going to assume, you notice here that they did not assume that everything was in tension. They drew FBC in compression. That's fine. Again, you can draw them in whatever direction you want, but the typical convention is to assume tension for everything until proven otherwise. All right, steps for analysis. First, we start with an FBD for the entire system, which allows us to find the reactions and get a global perspective for what the system is doing. Then we do each of the joints. Which joint? It really depends on you. Wherever you want to start is fine. You don't have to solve, you typically don't have to solve n joints to figure out what all the forces are. You can do n minus 1, but the last joint serves as a way for you to be able to check, right? So we'll do some of those in a little bit. The decision of which joint to start at should be driven by what you can solve. So if you have two equations, how many unknowns can you solve maximum? Two, right? Two. So if you go to a joint that has three joints popping off of it and you only know, and you don't know anything other than the force going into it, you probably can't solve that one yet. So look for places where you have two unknowns to start and then move around from there. Right? As you solve, redraw FBDs and continue to move. Solve forces in the X and in the Y for unknowns. You solve for your unknowns, and then you rinse and repeat until you have all of the forces that you were asked to find. Okay, great. So let's talk about the idea of a zero force member. Okay, so if I'm looking here and I analyze joints A and D, what do we discover the forces in AF, AB, and DE need to be? Okay, so I'm looking at joints A and D. All right, notice this is 90 degrees here, right? This is just some random angle. But specifically, I'm asked for AF and AB, right? And DE. Interesting question. Well, the force is being applied here, right? And it's straight down here. Okay. Notice that we have a roller at B, right? So a roller at B is going to give us a vertical force or a normal force at B, right? Let's do this real quick. Just to remind us all, all right? Here's BY. We have FX and FY. Okay, weird. So what do we have to do here? Okay. If a joint has only two collinear or two non-collinear members, then there's no external load applied or support reaction at that joint, then those two members are zero force members. Okay? So if they're not in line with one another and there's no reaction or external force at that joint, there's no force. Another way of thinking about this is look at point B. Okay? You have a force going up this way, one coming up here, and two coming out to the side. The only applied force at joint B is the reaction that is completely vertical, right? If I were to sum the forces here in the y direction, I only have two things, that two ways this can transfer. In the x direction, the sum of the forces in the x direction is zero, right? There's no forces being applied in the x direction. Okay. You can prove these, and we will, right? In this example, DE, DC, AF, and AB are all zero force members, right? So DE, again, pulling down at P, straight down. This has, if you look at C, right, you're going to have Y components here and here, right? But no, anyway. So we'll go through and we'll prove some of these in a second, right? You can easily prove these results. Why is this a big deal? Because then you can remove all of your zero force members and simplify your truss, right? So you don't have to worry about them. I told you guys, I think, last time we talked about this, maybe. Um, I had a statics professor who had been teaching statics for probably thousands of years by the time that I got to him. Okay. Um, very, very likely thousands of years. And he was so, and he was a civil engineer and he had his PE license, right? And so the guy had a tremendous amount of experience in the design and analysis of trusses, right? And he would just look at things and be like, yep, that's what the answer is. Okay, move on. And he wouldn't really explain any of it, right? And so here's the thing, zero force members are nice if you start to understand where you can pick them up. They simplify what we are doing, right? They simplify how we can go about our analysis, but it is not necessary, right? And you can prove them out. And what we're going to do, the way we're going to approach this in some of these problems is I'm not going to tell you up front what the zero force members are, but when we get to them, I'm going to prove why it's a zero force member, and we're going to talk about why you would have the intuition to make that happen. Okay? But something like this it's a little bit trickier to use as an example, right? But again, if you look here at point A, right, this becomes a zero force member, not because there's no force coming in the y direction, but because it's all taken up by this crossbeam. Okay? It's all taken up by that crossbeam. Okay? If three members form a truss joint for which two of the members are collinear and there is no external load or reaction at the joint, then the third non-collinear member is a zero force member. All right, let's look at DA here. Okay? Three members make a truss joint, right? At joint D, we have three members there, right? Two of them are collinear, right? There's no external load or reaction at joint D, right? Joint D is undisturbed. So again, zero force members are not absolute, right? I can have a zero force member in one configuration, but if I change where my forces are applied, that zero force member is no longer a zero force member. It is completely dependent on the loading of our truss, right? If I had a force at point D, DA does not become a zero force member, okay? But look, so if I'm pulling at P, right? Clearly there's an X and a Y. There's some component that comes from here, right? I have a joint at A, so that's a rocker, right? So, but at P, I clearly have some force that's going to be transmitted down E all the way to B through those members, right? Because member ED and DC are collinear, they have to have the same amount of force passed through since there is nothing applied at D. And so D to A becomes a zero force member. Okay? Think about it this way. Those are at 90 degrees, right? If I flipped my coordinate axis to be be X along member this way, right? Along members ED and DC, right? And Y coming up vertically. If I were to sum the forces in the Y direction, there is nothing there to balance dA with. And so dA would be zero. We can prove that it is a zero force member by doing the statics at that joint. Okay. Zero force members, so again, right, zero force members are not absolute. And so in practice, we can have zero force members, they aid in stability, but they are not always zero force members if the loading were to change. If somebody goes up on this truss and starts standing on point D, dA is no longer a zero force member. Okay? Same thing goes here for C to A, okay? Why? Because these are collinear. There's nothing applied at C. So this is a zero force member, okay? You can see the redrawn truss down here where you can move those, okay? Again, same deal though. If you were to sum the components, if I turn my coordinate axis, right? So let me draw it so it's a little bit clearer. If I draw my coordinate axis, maybe, oh, it's down there, cool. To be like this with X and Y, right? So now it's along there, right? If I sum my forces in the Y direction, you're going to have some component in the Y direction, but that's the only thing in the Y direction, right? So when you, what's 0 divided by the sine of theta? Is 0. So your magnitude is still 0. You can prove it. So does it simplify things? Yes, if you can do it up front. Is it necessary for your success for solving problems? No, it is not. And if you have any questions about whether something is a zero force member or not while you're working through problems, I would recommend just do the statics at the point and see what happens. Right? That's what I would suggest. Okay. So let's walk through this one, right? We talked about it, but so we're going to analyze DNA, right? Or did we already do this? We already did it. Okay, great. Cool. Let's just do this. Let's do this problem. Where is it? There we go. Very good. Did we do this one last class? Do you guys have this in your notes? Okay. I just want to make sure. No, you guys did this one last time. Okay. Excellent. So determine the reactions and forces in all the truss members. Do not forget to mention whether they are in tension or compression. All right. This is going to be the pretty much the standard for the homework for stuff. It's about structural analysis, right? Trusses. Is this homework for? Yeah, this is the homework for stuff. Yeah. Okay. Okay. So method of joints, method of sections, right? Method of sections next class. So since this is method of joints, and typically when we're asked to determine the reactions and the forces in all of the truss members, that's going to require us to do method of joints, right? If you're asked to find everything, method of joints is your method of choice. If I want the reaction forces, well, the first thing that I'm going to do is draw a free body diagram for my entire system, right? So I find it easiest to draw all my points first and then connect them. But you guys can do whatever you want. All right. Point A. What kind of reaction do we have at point A? What kind of joint do we have there? A pin. What do we have at B? Pin. That's gross. Because that's four. That's four. So how are we going to handle that? Because we want three, right? Because this is a full FBD. I got it's a 2D problem. I got three equations, three unknowns. Let me complete my truss here for fun. Yeah, so we're going to use a trick that comes out in our favor to reduce the number of unknowns. And it's fine. You can do this. It's totally legal. I'm just going to call this FA and say that I know it has to be pointed along the member. Sure, you say so. This is 6 meters. This is 4 meters. And this is 4 meters. We have some applied forces here. 900 Newton and 600 Newton. All right. So we get three equations, and that's great. I'm going to call one thing out here before I do anything else. Notice that this is a 6, the full total from, if you did the triangle ADB, right? That is a 6-8 triangle. Some people would call that a 6-8-10 or 3-4-5. Recognizing that this is a 3-4-5 triangle is really helpful for later. Or you can find the angle if you want. It doesn't really matter. So if we're going for reactions. Let's start. Sum of the forces in the x direction is equal to 0 is equal to bx minus 900 minus 600 plus the x component of A, right? And the x component of A is going to be 3/5 of FA. Equation 1. Do the same thing in the y direction using the components. It turns out that we're going to need a moment equation. Where would you guys pick to take the moment? I use point B. Using the DiGregorio principle of where to pick moments, I pick point B because BX, BY, and FA in the X direction all pass through point B, eliminating 3 of my forces, meaning that I don't have to write the moment for more than 3 of these forces. Okay, if I want the moment as established by 900 newtons, that's positive 900 by 4, because if I were to have this and push with 900, it goes in the positive rotation direction. Same deal with the 600, will also be positive, but that one is 8 meters away from point B. And then the final one that we have is A. A pushes up, right? Or from this side, by your perspective, right? So that's going in the negative direction. So we will subtract the y component of FA times 6 meters away. We can solve this right away for FA, right? FA, and that cracks open the rest of the problem, right? So that gives me 1750 Newton. So it's 900 times 4 plus 600 times 8 divided by 6 times 5 quarters is obviously 1750. I mean, it's like asking what 2 plus 2 is. All right, easy. This came out positive, so means that it is in fact directed up and to the right, right? Okay. Substitute that in to equations 2 and 1, and you can solve for by and bx, right? Giving me a by of negative 1400 Newton, which means that this is actually pointing downward. And it has to pull it down to counteract the upward force from FA. And BX is 450 Newton. And that is pointed to the right. So FA and in the X direction and BX in the X direction counteract the two pushing to the left. Now we do the fun things. Okay, where should we start our method of joints? Where would you guys like to, right? I'm going to keep these reaction forces up at the top while we do the rest of this. So if you could pick any joint, where would you guys go? Point B? I mean, you could do point B, sure. Right? You've got C, BC, and BE. What are some reasons why I wouldn't want to do that directly? It's not too many forces. What's What do we know? Do we know anything about the angle that this is at? Not really. We know that it's 4 goes we know that's 4 in height, but we don't know. I mean, we can maybe assume that that's a 3, 4, 5, maybe. Looks like it's halfway. I can't really tell. But you could do it for sure. Um, I mean, C has 3, so C is probably not the best one, right? We know that's not a zero force member right off the bat because there's a force at C and 2 that are collinear, so all of these have to be taking load, right? D has 2, right? So B and D are looking pretty good. E, not so much. E's got 4 different forces there. You could go A, right? A's only got 1, so it's really not interesting at all. It's going to generate. Guess what? We're pushing along A in this direction. All that force just goes right up to E. FA is FAE, or should be. Okay. I started at D, but you can start at B for sure. For sure. All right, so let me draw my free body diagram at D. Here's joint D. I'm going to have FDE coming down this way. Named cleverly because it goes from joint E to joint D. I'm also going to have a force that comes straight down called FDC. And we have an applied force there of 600 Newton. And just to remind ourselves, X and Y in these directions. Okay, we don't know, right? We don't know either of these forces, so let's start with our sum of the forces in the X direction. I'm going to sum the forces in the X direction, set that equal to 0, and that's negative 600 minus, well, we know this is that same triangle that we're using before. This is a 3, 4, 5 for sure. So that's got to be 3/5 of FDE. So we can find FDE right off the bat. So FDE is negative 1,000 newtons, which means that FDE is equal to 1,000 Newton compression. We picked the wrong way. So if we are going to move, when we move down to joint E, we will rectify what that looks like. We will draw it actually in compression because now we know that it's in compression. What about FDC? Okay, well, some of the forces in the y direction are equal to 0. Is equal to negative FDC minus FDE. That's the 4/5 portion of it. All right, so FDC is equal to negative 4/5 FDE. Remember when we are doing these equations, right? These are scalar equations. So you're just putting the magnitude of FDE in there. You don't put the negative sign in there with it. No, sorry. You do. Because we drew it incorrectly, you put the negative sign in there with it. Okay, my bad. So it's negative 4/5 times negative 1,000, which comes out to 800 Newton, which is tension, right? So F DC 800 Newton tension. All right. Okay, so now we've got FDE and FDC. Let's move down to joint C. Move into joint C. What do we have at joint C? Well, we've got an applied 900 Newton here. Then we found that FDC was in tension, right? So we will continue to draw it in tension, FDC. We also have an unknown force here that we're going to call FBC. That will be assumed to be tension. And this one is FCE, which I'm going to assume to be in tension, but I would argue is pretty obvious that it's going to be not in tension. This one is a pretty easy one if you're just looking at it, right? Because FBC should equal FDC, and FCE needs to counteract that 900 newtons, right? The X component, since it's pure X and pure Y, it transmits in that way, right? And so if we were to do the math, which we will, because that's kind of why what we're doing. I should probably go to the next slide so I don't have to keep truncating what I'm writing. So let's sum the forces in the x. Negative 900 minus FCE. That's in compression, right? So write it down up here. Notice that when I report it, I don't report the positive or the negative. I'm telling you, hey, it's compression or it's tension. That's enough to understand. Okay, so when I write it down up here. So that means that that's actually pointing the other way, which makes sense because, again, two of the members are completely north-south, two are completely east-west. They have to balance each other, right? So if we sum the forces in the y, we get FCD or FDC. Let's call it FDC, I guess. Minus FBC. So FDC is equal to FBC. Which makes it 800 newtons in tension. So far, we have this guy, and this guy, and this guy, and this guy. All right. So now and I would also argue that we have FAE, but we'll use that as a check in a second. Because I'm gonna go to joint E now. Why am I gonna go to joint E? Because I can just finish this right off the bat with joint E. Joint E is going to require us to make an assumption that's not drawn here, but we're going to assume that that is 3 meters. So that this triangle is also a 3, 4, 5. Yeah. How would I know to do that otherwise? I mean, you're kind of forced into it at this point because there's not enough information given. Based on the way this is drawn, I think it's a reasonable assumption, right? Could you do all of the geometry? Whew. I mean, yeah, you could, right? You could figure out this angle and then know what that angle is, right? Then you can use this angle because you know that these two angles are the same. And so then you know that this has to be 90 degrees maybe, right? I mean, you can work your way around to figure out what the actual angles are. I think it's just safe to assume there's a 3, 4, 5. 4, 5. All right, so let's draw the picture of the free body diagram. Okay, point E. Point E, we have FCE, which we know is in compression. We have FDE, which we also know is in compression. FEB. And FEA. Okay, we know that all of these are 3, 4, 5s, right? 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 3, 4, 5s Okay, great. So now what? Well, let's see what we got going on. So sum the forces in the x direction is equal to 0. So now this is going to be a lot more trig, right? We have negative FCE minus 3/5 FDE minus 3/5 FEA plus 3/5 FEB. Does everybody see? Very comfortable with that. We know two of those quantities, but we don't know the third. So we're going to keep going. We're going to need the second equation. Two unknowns still. In the y direction, well, we have negative 4/5 FDE minus 4/5 FEA minus 4/5 FEB. 4/5 are all just go away, but we'll get there in a second. So in this case, we're going to have to solve one and plug it into the other, right? So we'll solve equation 1 for FEB. Doing so tells me that FEB is equal to 5/3 times FCE plus 3/5 FDE plus 3/5 FE. Why did I choose to solve number 1 for FEB? Well, because everything else is negative, and if I just move it over, I don't have to deal with negative numbers. It should just all be positive, right? That's why. No other reason. The nice thing about the 5/3 is that it'll cancel this and this, right? And so if we wanted to rewrite it as 5/3 of FCE plus these things, we could. Or you could leave it also. It's fine. Let's plug in some of the known values, right? FEB is equal to 5/3 FCE plus, well, FDE, going back up here, is 1,000 plus FEA. FEA is unknown still, right? No, we got FEA, did we? FCE, thank you. Looking in the wrong spot. 5/3 of 900, which is 1,500, right? Yeah. But this gets us what we want, right? We're able to see that we have FEB in terms of FEA, so that when we plug that into equation 2, we have everything just in terms of FEA, solve for FEA, get a value, come back, plug in. All right. If we really wanted to get fun with it, we would combine these and you get 2,500 plus FEA, right? Just complete it out. That makes things a bit nicer for us to plug in, and then when we come back, we can solve it pretty quickly. Okay, so let's plug this in. Equation 2. All right, so I will, let me know if you guys can or cannot see this. Right. Okay, I'm going to take this. Before I sub anything in, I'm going to take the 4/5 out. Is right. If I multiply both sides by 5/4, they go away. So we're just gonna make them go away. So let's do that. And 0 is equal to negative FDE minus FEB, but FEB is 2,500 plus FEA, and I'll put that in parentheses, minus FEA. Mhm. At first glance, that looks like the FEA is cancel, but they don't because negative is in front of the parentheses, so it's actually subtracting FEA when we distribute it through. Rearranging this, and I'm going to put that, I'm going to move our result here up and erase the rest of it because I need more room. Keep that. So moving this up, right, we can continue to, let's move forward with this. We're going to get, what are we going to get? All right, FDE is, so we'll say FEA is equal to negative FDA minus 2,500 minus FEA. Right? Pull that over, make that a 2. Okay. This is 1,000. Check this out. It actually checked out our work for us, right? What was the reaction FA that we got? 1750 along AE. So we're feeling pretty good. And we know that it has to be pointed in that direction towards E, which would make it compression. Right? So that checks out based off of our FA. Right? We can run a check for this by using joint B, since we didn't use joint B, right? So you would do this one of two ways. You would either assume that you do not know the reactions and solve for the reactions, or you will sum all of the forces in the x direction and make sure that they equal 0, right? So let's run a check using joint B. But before, well, right. Everybody good with this so far, right? Time consuming, tedious. I would argue not particularly difficult. The setup is tricky if you have to figure out geometry, for sure. But otherwise, I think you guys are all capable of running through this. It just takes time. It just takes time. All right, joint B. Here's joint B. We'll do it this way where I know what BY and BX are, right? Okay. And then we also know FBE, which I didn't write down. No, I guess I didn't write it down. FBE came out to be 750 newtons in tension, correct? We didn't solve it last time. All right. I erased it before we solved for it. We had to plug back in to get FBE. My apologies. I was so focused on FEA. So where did that come from? Let me run it back real quick to show you. This is, come on, we'll get there. Big reveal. There you go. 2,500 plus FEA, right? Remember, FEA is negative, right? Because we drew it going in the wrong way. It's negative 1750. 2,500 minus 1750, 750. Make sense? Or if I can write it correctly. So we put, we take this and we put it in here. Yeah. Once again, this value, negative 1750, goes in here. And that's where we get our positive 750 newtons in tension. Okay. Yep. This is where I live now. No? Okay. That's all we have. Very good. Perfect. All right. So now I got FBE, which is 750 newtons. And we know that that is a 3, 4, 5 triangle. And we also have FBC. FBC, we know, is also tension, right? And that's 800 Newton. Very interesting. So let's start off. We'll sum the forces in the x direction, and that equals 450 minus 3/5 of 750. Okay, 3/5 of 750. That's 450. Oh my gosh, it worked. Let's sum the forces in the y. Negative 1400 plus 4/5 of 750 plus 800. Okay, 4/5 of 750 is 600 plus 800 minus 1400. Did it. Check complete. That's the easiest way to check. If you wanted to check that you actually found the reactions correct, you could do that too, right? And make those BX and BY, right? But you already found, you did that the first thing, right? So, you know, now what would happen if you found out that that wasn't zero? Well, it means that you did something wrong. Um, so you got to start hunting. So I would start by looking at your reactions, make sure that you did those correct. Because if you did those incorrectly, right, the rest of these calculations don't really depend on those reactions very much, right? We didn't really use them in any of the calcs that we made. So hopefully not too much else is messed up. But you're going to have to walk through your process, make sure that you got everything documented correctly. Okay. What time is it? We got 30 minutes. Man, time flies, I tell you. I want to try something. All right. We're going to try something different today because reasons. Does anybody have any questions on method of joints so far? No? Remember, Find the reactions, go through the joints, right? Sum of forces X, sum of forces Y. That's where we need to be. Okay. So we're gonna try something different. Like I said. So before we do that, share this problem with you guys. If you want to go back and try to do this one, this is a good practice problem to do. We're not going to do it right now because I want to try something different with you guys real quick. But here's one that you might like. Okay. This is what we're going to try today with our remaining 30 minutes, and I think we have enough time if I can unfreeze the video. Okay. Okay, this is what you're gonna do. You're working your rows. You guys are gonna work together in your rows to do specific tasks. Okay, row one, you are going to work on finding joint D, the forces in the members attached to joint D. Row two, you're at joint C. Notice some of you might need input from other groups. Row three, joint B. Row four, joint A. And row five, you're going to find the reaction forces of the entire thing to start. Okay? So we're going to work on this right now. So get together in your groups. Ideally, well, not ideally, you're going to determine whether or not these members are in tension or compression. Okay? Row five, you're going to need to go first. Okay? Because some people are going to need your stuff. Uh, actually, yeah, the row four is going to need you guys to be helpful because otherwise they're going to have too many unknowns. Sorry. Sorry. Row five, you go. You guys got to be working on reactions. Give your answers to the groups when you find them. Right. Everybody else start working. Get equations so that when you are tasked with when you get the answers from the other groups, you will be able to move on by just plugging in. All right. Mm-hmm. I mean, if you gotta go, you gotta go. But I mean,
Would I miss participation?
but yeah, this is participate. Like doing this is yeah. You guys are expected to talk to one another and work together. Hence why the whole row gets to do it together. I bet you are. Mhm. I want you to find the forces. Yeah. I want you to solve for the stuff at joint D for. Yep.
This is what you do for just.
No, I want you to do the full process as a group. If you need to talk to another group to get results that you need to solve for portions of your FBD, you should talk to that group for sure. Yep. Yeah.
Does the ratio still work if I divide it into one of these divided by two? Then it'd be like a 2, 3 amount of time.
I mean, yes. Because when if you made it a 6-4 or you made it a 6-8-10, it's the same as a 3-4-5. So it would work in the opposite direction as well. Hmm. You, if if they're collinear and there's no external force applied at the joint, then yes, they would always be equal. Think about it like the same way that like if you had a piping system, right? Like water is that's poor analogy because there's a lot more stuff that goes into that. So yeah, the way that the force vector works, there's no reason for the vector to change direction if you're not applying anything at that node. Right. Yeah. Yeah. Remember, it's really what it is. It's an exercise in determining resultants, right? And so that's really what we're doing is we're using the components, but at the end of the day, you could find a resultant force at that node if you wanted to.
Like I said, we did a conversion.
All right. How you guys doing? We have about 10 minutes left. What did we get? You guys still working? We got answers? Row 5, did you guys finish reactions? Yeah? Since we got 10 minutes, let's go through it. All right, so someone from row 5, right? We got reactions here, right? So what'd you do? How'd you get the reactions? What did you get for the reactions? Let's start there. What did we get for the reactions? Somebody, don't be shy. Just tell me the numbers. What'd you get? How many reactions are there? Let's start there. How many are there? 3, yeah, but row 5 specifically. That's what I need. I need some, since row 5 found the reactions and they told me that they found the reactions, it would stand to reason that somebody would be able to tell me what they are. Grant, what you got for me? What's up? 3 actions. What are they? Sure. Right? Because you got a roller and a pin, right? So how did you find these? What did you do to find them, right? You probably drew a free body diagram, I would guess. You had something that looked a little bit like that, right? Um, yeah. Guess I drew the wrong one. There you go. Okay. You had a force here of 300 pounds. Then you had yeah, something like this. Yeah. Look about right. All right. So from there, what'd you do? How did you find them? Yeah. Right. Nice. And those look good from a positive, negative standpoint. Is everybody cool with that? Right. So when you solve for BX, right, you get what? 300 times 4 divided by 3, 400 pounds. And it came out positive, so you have it in the right direction. So you're going to keep it to the left. Great. Good stuff. Then what? What did we do after that? Sure. Okay. Cool. So we got to flip the direction of that one, right? So this is actually 400 in that direction. That makes sense because if one's going one way, the other one's got to be a couple, right? Pull it the other way. Great. Then the final. Great. And that makes sense to us because that should be counteracting what's pulling down. Right? Great. Awesome. Good stuff. I did the same thing. I except used the moment at B. Same deal. Only difference in how I did it and how you did it is I got a X to be to the left and BX to be to the right. But it doesn't really matter from a statics point of view. You can, as long as they are equal and opposite, that's all that really matters. And it won't affect what happens later. Cool. Good stuff. Thank you. So next up, since we did that and we got all that good stuff going, where should we go next? That's a great question. I'm going to leave those forces up there. We're going to go to row 3. In row 3, you guys did joint B. So joint B, what do we got? Probably you started with a free body diagram, right? And you got the reaction forces from row 5, maybe? Based on these reactions, right? Maybe you had it in the opposite way, but we'll use what row 5 has given us. And then should have something like that. We'll call this one FBC, and this one FBA. That's joint B. Okay. Someone from row 3. What are we doing? What's our first step? Yeah, right. So, okay. Okay. Yep. Yeah, you got it. So yeah, you got that, right? And so you had it going positive, right? Just to reflect what we were saying here. That's fine. And so you solve for BX. What'd you get for BX then? Or no, you solve for FBC, sorry, not for BX. Well, yeah, this would be 400 times 5/4, so it's 100 times 5, 500. And that tension or compression? What happens if we do it with a negative here, right? Well, then you end up with FBC, right? So we have a negative BX is equal to 4/5, right? So you end up with negative 500. So if you had it there, you would have to flip to compression, right? So if your reaction is pointing the other way, it flips the sense of tension or compression, right? But the number stays the same. So if it is drawn for the way that Barrett discussed it, right? We had it drawn that way, right? Again, AX and BX they can be flipped. All that's going to do is change which ones of these we have in tension and which ones we have in compression. It will cascade throughout the rest of it, right? But that's fine. Okay. Great. Now what? Well, should probably sum the forces in the y direction. You had by minus 3/5 FBC minus FB. All right. So what is FBA then? Well, we got 300 minus 3/5 of 500. All right, so this is 300. Interesting. 0 pounds. We found a zero force member. How are we supposed to know by inspection that that's a zero force member? That's a tricky one. It's a tricky one because there's external forces applied at the joint, right? It just so happens that that happens in this case. It's not necessarily one that you're going to be able to pick out. What if we had used 400 pounds at point D instead of 300? No longer a zero force member, right? Because 3/5 of 500 is certainly not 300 pounds, right? So just so happens it's not one of the ones that we would necessarily indicate. Okay, great. So we got that. We got FBC. We got FBA. It's looking good. What next? Next, we're moving. We are moving somewhere. Where are we moving? Row. 1 second. Be ready. I know we're going over, but we're doing this thing. Row 4. And row 4, if I remember correctly, you have joint B. Joint B. Yeah. That B. Yep. Wait a second. Row 4. So we did 5, 3, 4. Joint A. That's the one. All right, let's do joint A. Well, so we got a free body diagram at joint A. This one's interesting. Right, so we've got, in our case, we've got some AX. We got F, A, D. You guys just told me that FBA was 0, so I'm not even going to bother drawing it. We've got FAC over here. We're almost done. All right, so row 4. Did you guys have this? Well, if we drew the other one that way, we will flip them in our sense since we just solved the other one that way. So there, we're gonna flip these. Okay. All right. What's going on with this? Row 4. What am I doing? Direct me. The whole row of row 4. You're like the most full row out of all the rows here. Anybody. What do I do? You have like 50-50 shot of the things that you're supposed to do here. It's actually better than that because you know for a fact that there's 2 things that you have to do because it's method of joints. So it's method of joints. What do we do? If we don't know what to do, do something, right? So what are we doing? I already drew the picture. What's the next thing that we do after we draw the picture? Sure. Sum the forces in the x and the y, Sam. So which one do we do first? X or y? Or x. All right, great. So what does that give us? Cool. What's that? I didn't include the horizontal component of FAC. Oh no. Oh no. Man, I didn't do it. Oh my. What is the horizontal component of FAC? It is over. But we're finishing this problem. And it's going to take as long as it takes because I have nowhere else to go. And frankly, right, it should, like, we've got 2 things left to do here. It's not very difficult. Um, so what is the X and Y components of FAC? Okay, great. That doesn't help us. I know FAC. So what's in the y direction? 3/5. Are there any other components in the y direction? How else are we supposed to know that? That is one of the ones that we're supposed to know, but not by looking at joint A, but by looking at joint C. If you look at joint C, what happens? Let me show you. They are collinear at this point, right? With nothing being applied at C. So FAC is 0. We went at it backwards, but there we are. Okay. So now we know FAD is just equal to AX, right? Which means that it's going to be, so it's negative FAD, excuse me. Negative FAD is equal to negative, or FAD is equal to negative AX. So FAD is equal to 400 pounds in compression. Okay. We have to do one more, and then we've got all the forces that we need for this. And it's going to be row 2. Row 2, you guys had joint C. So let's talk about joint C. Here's joint C. I know these forces should be pointed in these directions. What's that? CB, BC, and FCD. FCA is 0, so I'm not even bothered drawing it. Let me ask you a question. What is the missing force? We know FBC. What is it? FCD, right? And what does it equal? So I want you to look at this for a second. What if I used a different coordinate axis just for this part, just for this free body diagram? That would be an interesting trick that feels like cheating, but isn't. Because remember, coordinate axes are arbitrary, and you get to choose them. And this one makes it really easy to see that if I sum the forces in the x direction and set it equal to 0, I get negative FCD is equal, or pardon, plus FBC is equal to 0. So FBC is equal to FCD, hence up here equal FCD. And we finish it. And then row 1 can do the check, right? Because if we went through it, we could check out and make sure that everything equals 0 at that point. Or you could take out the applied force of 300 pounds and check that that equals what it is. Yeah, cool. Thursday, I won't be here. Just reminder, Professor Tomford will be here. Please, she will talk to you about method of sections. It will be glorious. Mhm. With the FBA, why isn't that there? Um,